So first of all, let us quickly recap that in the previous video where we gave an analytical proof of the infinitude of primes, we showed that when p is greater than 1, the logarithm of 1 plus 1 over 2 to the power of p plus 1 over 3 to the power of p and so on. So this series we denote by zeta of p. So we showed that the logarithm of zeta of p is less than 3 over 2 times the sum of the reciprocals of the pth powers of the prime numbers. And that was when p is greater than 1, and we let p go to 1, knowing that this series diverges when p equals 1 to show that this series diverges, and so that there must be infinity many primes. In this video, we are going to use this result to conjecture the prime number theorem, which is a result about the asymptotic behavior of the number of primes up to any given positive integer. So this is only going to be a conjecture of the theorem. It is not going to be rigorous in any way. So if we divide both sides of this inequality by this series on the right, then it becomes logarithm of zeta of p over the sum of the reciprocals of the pth powers of the primes is less than 3 over 2. And we recall from a video on the Euler-Mascheroni constant that the sum of 1.5 and so on plus 1 over n minus the natural logarithm of n converges to a real number called the Euler-Mascheroni constant, which is greater than a half and less than 1 as n goes to infinity. And when we consider this result and the result above here as p goes to 1, we think that perhaps the sum of the reciprocals of the first n prime numbers minus log n might possibly converge to some real number c. So this is not a rigorous implication or anything, it is just a conjecture. We hope to obtain something like that, or we see where assuming this leads us. And when we assume this, let us first realize that the derivative of log x is 1 over x times log x. And so log n can be written as the integral from e to n of 1 over x log x. So that this thing that we have conjectured here can be rewritten in this form. So 1 plus a third plus and so on plus 1 over p sub n, which is the nth prime, minus the integral from e to n of 1 over x times the natural logarithm of x as n goes to infinity is equal to c. So I've put an interrogation mark here because we have not proved this, we are just assuming this to see where it leads us. So the reason we've rewritten this as an integral is because we want to compare it to the analogous statement where we are not considering just the primes but all the natural numbers. So this result here is established. We have already proved this in a video on the Euler-Mascheroni constant gamma. And we want to compare these two statements to see where it leads us. So if the sum and the integral are truly connected as we want, do the summand and the integrand become comparable as n goes to infinity? So this is something that is suggested by our result. And in this case, this would mean that the nth prime would be asymptotic to n times log n, because these are the summand and the integrand. And that is asymptotic means that the ratio of the nth prime to n log n goes to 1 as n goes to infinity. So is this the case? Well, this result is equivalent to saying that in the first n log n natural numbers, there are about n primes. That is, as n goes to infinity, the ratio of the number of primes in the first n log n natural numbers should be equal to 1 in the limit, which is that in the first n natural numbers, there are about n over log n prime numbers. And this can be rewritten as pi sub n is asymptotic to n over log n as n goes to infinity, where pi of n denotes the number of primes up to n. And the asymptotic again means that pi of n over log n tends to 1 as n tends to infinity. So none of this was rigorously proved in any way in this video. It was just conjectures, and the conjecture has led us to trying to show this result. It is quite difficult to prove this rigorously. It is only very much later on that we will prove the prime number theorem in another playlist. But let us try to put various values for n and calculate this ratio. So we see that when we give larger and larger values to n, this ratio indeed seems to be tending to 1. So very well. So the one thing that we can conclude, at least from all this discussion, is that all these conjectures started when we began to study this function zeta of p, and it would really seem profitable if we went even more deeply into the study of this function. So this is what we will be doing in the next videos in this playlist. It is worth noting that in this playlist we are restricting p to be real, but in another playlist we will allow it to be complex.